Okay, so it's my instrument, Laurent Cantier, who's going to talk to us today about webbing transformations and C-star algebra.
Okay, thanks, Tristan, for the introduction. And yeah, so today's topic, I wanted to introduce some recent construction that I did, and so it's going to be little sister algebra. So maybe for some people this is going to be nice, but at the end of the talk I will apply all that I'm talking about to actually classification of sister algebra, and I will start with some motivation for this work. So recently, so namely last year and the year before that, two new invariants have appeared. So there is the unitary Kuhn-Samy group. The year after this, so this was 2021, and the year after that, total Kuhn-Samy group. So those are new invariants that are mainly aiming to classify non-simple stuff. Okay, so invariants for non-simple sister algebra, and the construction are, in that case, both cases done for separable and stable rank 1 sister algebra. Okay, so I will explain how and why they were created, and but the main motivation for these webbing transformations is that those two are really alike. Okay, so they are constructed in the same categorical way, in a sense. And so the point of this webbing transformation is to kind of systematically study this type of construction and see if we can create more invariant for sister algebra. Also, one of the advantages to do this in an abstract setting is that we can get rid of those conditions. Okay, so far those two invariants were only defined for this. It's a rather large class of sister algebra, but still it's kind of a restriction. So we want to generalize systematically the above construction. So the main advantage is that we extend the existing ones, which are those two, to general sister algebra. Another point is to really nail down in which category those invariants fall into, and we're gonna define and study the codomain category of those invariants. And in the end of the talk, if time allows, I will define a new invariant for sister algebra, make a nice conjecture, and hopefully it's some work we studied with Bishan, it will verify to be true. Okay, so so I didn't really say who were those guys and all of that. That would first take a while, and I will somehow, I want to describe to you this webbing transformation, and then tell you a bit more who are those two guys, because they fall out from this kind of construction in a rather nice way. Okay, so before I start, I also want to as part of motivation to give a quick overview of some classification result of C-star algebra. And actually, so I didn't mention, but so this was part of my PhD work, and this was done by Anne and Liu. And so, yes, so maybe it's a personal feeling, but giving this overview of classification result, I will stress out one of the motivation for the unitary semi-group in the first place, and namely is that codomain categories for invariant of C-star algebra that exist so far, which are really powerful, and I will explain some of those results. Sometimes lack a bit of consistency as far as purely category theory is concerned, not about the C-star algebra themselves. So let me recall some classification result. So on the okay, so the simple case is now most of you might have heard this many times, but it's kind of solved. Okay, so this was done by many people over many years of work, but I might just cite those two papers. Okay, so this is Elliott, Gong, Lin and New in 2015, and Tikuzis, White and Witter in 2017. Those papers are they're good. Yeah, I'll check from time to time. So when we speak about classification of C-star algebra, we speak about invariant, we mean functorial invariant. Okay, so in that case, so the Elliott invariant start from C-star algebra, and what could be named the Elliott category. I mean, there is no standard name as far as I know. And to a C-star algebra, we look at another group, which is the ordered K0 group with the unit, the K1 group, the traces, and some pairing map. Okay, so this is another abelian group, which I will denote by ab group U. This is an abelian group. This is a Choquet simplex. And this basically is a compatibility map between the K0 group and the traces. Okay, so already in that sense, I mean, we can ask the question, can we do better as far as the codomain category is concerned? Okay, so we get linear codomain category. Okay, and for the simple case, some work has been done by Antoine, Dadarla, Pereira, and Santiago in 2018, 11, sorry, where they show that this invariant with this codomain category is when restricted to simple separable. I think you need to have stable rank one also, Z stable, that this is naturally equivalent to another functor, which is a variation of the Kuhn semigroup. Okay, so and the variation, so to be explicit, so to a C-star algebra, we assign the Kuhn semigroup of the C-star algebra tensor the continuous function over the circle. Okay, this is a way in the simple Z stable case to recover the K1 information. I mean, yeah, okay. So this is not true in general, but upon restriction to simple Z stable, unital, separable, and I think unit stable rank one also for technical issue. Okay, so you might not be convinced, but this category is not somehow, this is the category of semigroup. Okay, there is a topology on that, and I will recall everything, but this category is somehow ad hoc, like it's constructed so that everything is well defined and it works. But you can see that there is already compatibility map that appear even in the simple case. And now to get you a bit more convinced that motivation for those two guys is that in the non-simple case, this gets even somehow, yeah, this category gets even more complex. Okay, so this is table rank one.
The second.
Dadarla.
Oh.
Okay, so yeah, so non-simple case, which is the case we are interested in. And some result has been obtained already in the 90s to classify non-simple C-star algebra using these kind of things, but now you have ideals. So the first idea that was developed by maybe Wang and Elliott, and afterwards by Thanks. And so those guys are classified by, I guess, what could be. Is it working? Yeah. This go back to work done by Steven, so I will just write the Stevens invariant to a system algebra. And again, this is not conventional, but let's call this category, this built on ad hoc category, Steve, and to A. So we have to look at, so AI is interval algebra. So K1 is trivial. Okay. So basically you just look at these guys and those guys. And you not only want to look at what's going on at the level of system algebra, but also what's going on at level of ideals, okay? And this ideal property, basically what it tells you is that you only need to look at corners of algebra, okay? You don't have to look at all the ideals. So now you look at things that look that way. So you have to look at list of things that are indexed by the projection in your system algebra. And now you have a lot of compatibility maps that appears. Okay, so basically this Steven category should be the object and the morphism in there. It's pretty awful. And usually when you look at papers that try to deal with the how to define this kind of category, it takes like 3 pages of commutative diagrams and everything. And now, so one can ask, what does it really mean? I forgot to say. When I say classify by the Elliott invariant, it means that two system algebra in this class are isomorphic if and only if their Elliott invariant is isomorphic. Okay. So same goes for here. But now, what is an isomorphism? Okay. So to me, I find it to classify system algebra, it still works well because we have some tools to know. And this thing, I mean, those invariants are pretty powerful. But as far as category theory is concerned, this is not the cleanest setting you can get. And so I will ask the same question. Is there like a nicer category and a nicer invariant that somehow get this information and give you some classification results? And in that case, again, the semi-group comes to rescue somehow. So this is a result by Robert in 2012. And he says that unital inductive limits of one-dimensional NCCW complexes with trivial K1 are classified by their Kuhn semigroup. Okay, so two things happen here. The first one is that we don't need to restrict to some nice case where we control what's happening with the ideals. So there is, okay, this might be weird to most of you, but just think that any unital AI algebra is in there. Okay, so it's a generalization of this result, and for even larger class of system algebra without this extra condition on the ideal. Okay, and again, so this is Cu is a functor from system algebra to this category Cu that I will detail in a moment. And to me, this is kind of the best result one can hope for when speaking about, classification. So we see kind of two different directions. One is to locate what kind of information do I need to classify my sister algebra, and then create a category on purpose that has all the compatibility condition and show that I have gathered enough information to classify my sister algebra. And the other one is kind of using this magical Kuhn semigroup and get all these compatibility conditions that are inherent to the invariant, okay? So you might ask why people don't use the Kuhn semigroup in the first place. It's because it has some drawbacks, okay? Kuhn semigroup is really difficult to compute, so we have very few. Now it's that more and more, but the Kuhn semigroup of the cis algebra is really hard to compute in comparison to the K0 or the K1 group, for example. Okay, maybe the threshold state space is also difficult to compute, but okay. So if people have these things for a while, is because there is a reason to it. Okay, but my point is now there are more complex and larger class of sister algebra that are classified by refinement of the Elliott invariant, let's say, where people have just shuffled more and more things into those things. And also one flow of the Kuhn semigroup is that more or less it captures what's going on with positive elements. Okay, so we get back what's going on at level of K0, we get back what's going on at level of traces, but there is no way to get back what's going on at level of K1. And more recently, it's been shown that the Hausdorff algebraic K1 also plays a really important role in classification. And this is, there are no way to get this from the Kuhn semigroup. So these two guys, what they were trying to achieve is to somehow incorporate this information that we know is necessary to classify some sister algebra, like smaller or larger classes. And can we do it in such a way that we preserve a CU-like type structure, okay? So in such a way that we merge this information that is missing from the Kuhn semigroup without somehow destroying this nice categorical setting. Okay, so the answer is yes. So let me first recall a quick overview on what this guy is. Okay, so overview on so definition. So the category CU is a subcategory of positively ordered monoid that I will write from. Okay, so you have a monoid that has an order and all the elements are greater than 0. And it's not only an algebraic object, you also have this topology that for people in set theory, it's kind of a domain, okay? Maybe sequentially domain, I think Tristan will agree. But we have also a topological flavor in this object. Okay, so objects are formed satisfying a bunch of axioms. So the first one is to speak the domain language. It means it's complete or directed complete. Okay, so every increasing sequence has a supremum. Second one, it's what could be called continuity or sequential continuity. It means that every element is the supremum of this is compact containment or the way-below relation that maybe we've seen enough so that I don't have to recall what it is. But yeah, basically all the topology is coming from that guy. Okay. So this is kind of completeness, continuity, and this is called, for those who study this thing, a domain. Okay, it's just sequentially domain, but okay. And O3 and O4 is that the suprema, the compact containment relation, and the sum are compatible. Okay. So compatibility between sum and way below, and sum and suprema. Okay. And the morphism, we ask that they preserve suprema. Those are morphisms that preserve those two extra structure. Okay. So why this category is nice regarding classifying non-simple stuff? So I guess the main point of this Kuhn semi-group is that we have an ideal quotient theory in this category. Okay, so we can define what an ideal is, and we can show that the set of all the ideal of a CU semi-group, when it's coming from a system algebra, is a lattice, and it's exactly capturing the lattice ideal of the system algebra. Okay, so yeah. Yeah, it means that if you have two pairs of elements, so you have S below T and S2 below T2, then the sum of the two small will be way below the sum of the. It's a monoid, so you have. Yeah, POM is positively ordered monoid. Okay. So remark, maybe with the time I will just go on and define an ideal in the more general setting afterwards. But so the category CU has what I call an ideal quotient theory. And therefore, it inherently captures the ideal structure of system algebra. So it means that intuitively, it means that everything you have to add into this category to classify non-simple things, you don't have to do it when you use the functor CU, but some variation of it, because it's going to be inherently contained in this codomain category. Okay, so yeah, as I said before, this result is kind of the best we can hope for. Namely, we just AI algebras, okay? If you go to 80s and you have some K1 that appears, and if you go to some more complex structures, then even K1 might not be enough. And so you need information about unitaries. And yeah. So now, so the point of those two things, so for example, I didn't explain too much, but the unitary Kuhn semi-group was to merge the information of K1 of all the ideas within the Kuhn semi-group without modifying its, let's say, nice structure of semi-group that has this kind of algebraic topology, which is referred to the Scott topology for those who know what it is. And the total Kuhn semi-group wanted to add this total K theory within the Kuhn semi-group, okay? So those two information, we know that they are needed to classify non-simple stuff under different assumptions, so different classes of system algebra. And so now let's forget a bit about system algebra and let's get into this Webbing transformation. Okay, so the main idea is to take the Kuhn semi-group as a base space. So I will have something like that, okay? And I want to enrich this semi-group with fibers, okay? More or less it's what will go on. And those fibers can be, so right now it's abelian groups, okay? And this is how I throw in, for example, K1 information or total K theory information. And I want to do it in such a way that I still get this this semi-group that has some algebraic and topological property. So I will not fall exactly into the Kunz category because now I will lose positiveness of the order, okay? All the elements that you get from in the fiber, they will not be greater than 0, okay? They will still have some weak positivity thing, but okay, so this is somehow the main idea. And let's start with gradually. So with partially ordered group systems. Okay. So I will first start to assume that my base space is just a poset. Okay, so partially ordered set. I just have an order there. And okay, so definition, partially ordered group system is a pair SG, where S is a poset, partially ordered set, and G is a functor from S to abelian group. Okay, so what does it mean that G is a functor with a domain S? So it's easy enough to see that S can be considered as a small category where the object are the elements of S, and the arrows are induced by the order. So namely, I have an arrow between the object S and the object T whenever S is smaller than T, okay? So between two objects, I either have one arrow or I don't have any arrow, okay? And now, another preserving map between two of those guys. Is also a couple. And so alpha is just the poset morphism between S and T. And eta is a natural transformation. So a natural transformation is from one functor to another functor that have the same domain and codomain category. So here I have to work a little bit around because my functor H is starting at T, okay? But I can pre-compose with alpha so that everything is working fine. So basically you have the first functor, which is G, from the small category S to abelian group. And I have this other functor, which is the composition of alpha with H, okay? And I require eta to be this natural transformation, okay? From G to H composed with alpha, okay? When I look at this as small categories, this is a functor, okay? Sending object to object and preserving the arrows because it preserves the order. So everything is consistent and I can compose maps, right? So if I have now another guy here, there is this natural way of composing natural transformation, okay? So there are some details to be checked out, but maybe, yeah, we don't have so much time, but it works, okay? So we indeed get a category of where the objects are those pairs and the morphisms are those guys, okay? And we have composition, the identity morphism and everything. And now I want to somehow from this pair to create this kind of object, okay? So I will do it in such a way, so okay, so the webbing transformation W is, so I didn't say, so we write the category of these guys in such a way, it's kind of a intermediate category, so it doesn't really matter if the name is, but basically it means that, yeah, I have a pair in poset and I have a functor from my poset to the abelian group category, okay? And to a pair SG, I want to create SG, okay? And I want to exactly get this kind of object. So SG is just gonna be the set of all pairs small s, small g, where small s lives in my poset, and g now lives in the abelian group obtained from the functor g evaluated at the object small s, okay? So I have a set, and how do I put an order? So I say that a pair SG is smaller than a pair TH exactly when they compare on the base space, okay? And since they compare on the base space, so this would be my S and my T, right? Now I know that I have an arrow here because S is smaller than T, and this arrow through the functor G generates, okay, an abelian group map from the fiber of S to the fiber of T. Okay, so I have a way to send this guy into the fiber of T where H is living, and I can check whether they are equal or not in this abelian group. Okay, so this is the group morphism from the fiber of S to the fiber of T. So with this group morphism, I can just send G where H is living, and I want them to be equal. Okay, you can check that this is a poset, the natural transformation. I can do this similar construction. Yeah, might try to go a bit quicker. And everything works out, and this is a well-defined functor, okay? So now so this is nice, and the thing is that my base space has more structure, right? So first of all, it's a POM, so it's a positively ordered monoid. And it has also this topological flavor. So the point is not to land in poset category, but to something that has more structure and hence it's more rich and capture more information. So Now, what if S is a POM? Yeah. So I will just, this webbing transformation will give me a poset on which I can create a sum that is induced by the sum given on the base space. Okay, so define a sum on SG as follows. So SG plus TH by definition. So I just sum the two elements on the base space. And here's some remark. I really need S to be not just an order monoid, but it has to be positively ordered to ensure that this guy in the base space is bigger than those two guys, okay? And if the order monoid is not positively ordered, maybe it's not gonna happen. So in this setting, it was fine. And now I have a way to send both G and H in a common fiber that is further away, okay? So I just send G to this bigger fiber and H also, and I sum those two elements, right? Okay. So remark, S in POM is necessary. Okay. Second point is that SG is not a POM anymore. Okay, you can take easy examples where your base space is, let's say, the natural numbers, and at each fiber, so you assign to the first fiber in 0 the trivial group, and all the other fiber are just the integer, for example, and identity maps between everywhere. And if you take any element that is not in the base space, it will not compare with 0. Okay, but we still have some positiveness. Okay, so yeah, I will definitely not define what they are, but still get weakened versions of positiveness. So I do get a webbing transformation from W to these pairs of POMs and functor into the abelian category into, okay, home star, it's something between POM and ordered monoids with this weaker version of positiveness, whatever that means, okay? And to a pair SG, you send SG, okay? And finally, what if S is in CU now, okay? Similarly, you can actually show that, not have time, but can show that the compact containment relation is entirely determined by the one on the base space. And this is enough to show that if your base space is satisfied this topological axiom O1 or 4, then so does your this monoid, okay? And yeah, so maybe theorem, I don't know. SG satisfies O104 whenever S is in C, okay? So a nice corollary from this is that I also can define a Webby transformation from these guys. So those are pairs where S is a Kuhn semigroup and G is a functor from S to abelian group. And similarly, I will end up into this CU star. So this is the same category. The only difference is that the order might not be positive, but you still get some other axioms that are like a weakened form of positivity. So for example, you don't have any negative elements. You know that you can always come back into the positive cone and so on. Those are technical details, okay? And the main point of all of this is that now I can show that all Webbing transformation are continuous. Okay, so this is not an easy proof. This is really somehow pretty technical. But for example, from this fact, I will show later that these two invariants that have been defined at the beginning, so the unitary and the total Kuhn semigroup, both had to make a lot of work to define them in the first place, and that's why we had to narrow down to separables invariant one case. And the continuity was really technical, and the continuity of the second one was based on the same argument, but somehow they had to do it all over again, okay? And now you just plug this Webbing transformation thing and you get continuity automatically, okay? Yeah. Okay, so yeah. I wanted to speak a bit more about this CU star category, so I will just quickly do so. So the category CU star is somehow a bit larger than the category CU, but you can still define so it also admits an ideal quotient theory, whatever that means. Model after the one constructed for CU. Okay. So there are some specific element or subset in a CU star semigroup. So you first have positive cone and maximal elements. Okay, so there are two continuous functor mu plus from CU star to CU. So namely, if we take a CU star semigroup that comes from this Webbing transformation, this is just recovering the base space, okay? And mu max get to abelian group, and this is somehow taking maximal elements, and somehow you get back the fibers, okay? So you have a way to recover the Kuhn semigroup and whatever case theoretical information you throw in this guy, okay? So yeah, then there are a lot of things. So you have exact sequence. Actually, so this might be important. You have this sequence is split exact, whatever that means. Okay, we are not in an algebra category, so one needs to be careful, but more or less the base space and the fiber are linked within this object, and this is where lies all the compatibility condition that were manually added in these other invariants. Yeah, I wanted to say more. So this category, I have been studied it in the same way the CU category has been studied in an abstract way, and most of the results that are available in the category CU, there is an analog result. Okay, sometimes want to be a bit more careful, but things more or less work out fine. And so in the last maybe 10 minutes, let me go back to classification of C-star algebra. So CU star is another monoid that satisfies this axiom 104 that I displayed earlier. Yeah. You have a partial order, but it's not positive. Yeah, exactly. Because the intuition is that some of those guys will never be positive. Okay. All of the guys from the base space are larger than 0. But the guys on the fiber usually they are not negative either, but they are just something else. Okay. And so now, okay, I left a lot of things in there, but anyway, we have a way to throw in any kind of K-theoretical information into the Kuhn-Semi group via this webbing transformation. And we have those nice results and theory. Okay, so the way to do it is via those CUK type construction. So if you give me K, which is an invariant from C-star algebra to abelian groups, so it could be K0, K1, algebraic K1, total K theory. You need some extra assumption, but K of the trivial algebra is the trivial group. K is continuous, but all of these things are kind of usual to ask for an invariant of C-star algebra. So now from this, I can just construct for a given slowly dying. So you can find two star homomorphism from the circle algebra into my favorite AI algebra. So that this happens, and I know, so now, yeah, maybe I should have defined it earlier. I defined the half-the-files unitary Kuhn semigroup to be CU. So now instead of putting the K1 group on the fiber, I put the half-the-files algebraic K1 group, which since 4 or 5 years drew a lot of attention and seems like a necessary ingredient to classification. And so you have that. But this does not happen. And hence, your star home are not approximately unitarily equivalent. And this is not direct, but as a corollary, you can show that the unitary Kuhn semigroup will not be able to extend Leonel classification results. Okay, this is not a trivial thing to see, but it seems that the right one that one should use is this one where the fibers are not just K1 groups, but half-the-files K1 group. Okay, so let me stop here. I kind of overlap the time, and thank you.
Awesome, okay. Okay, from then I'll ask a question. So these captions, right? Like supervising stable one. And so these things you're defining, the base space is still the Kuhn semigroup, right? So does this mean that you do have some way of defining a Kuhn semigroup for non-separable C-star algebra? Yeah, I thought that, I mean, you don't, I guess, you don't do the difference, but I thought things didn't work out quite as nicely when if you.
Yeah, so when I So yeah, when I first introduced this guy in my thesis, so and the separability and stable rank one, the Kuhn superequivalence is really nice, well described with the hereditary subalgebra and so on. And somehow I needed it to be able to send some guys, some unitary in the hereditary subalgebra, in the small one into the biggest one, okay? And now I kind of pass by this restriction. But otherwise, no, the Kuhn semigroup is defined for any C-star algebra. It's just that the yeah, so if you have a C-star algebra that is separable, then you get a real domain. That's the point. But if you're, yeah, exactly. So things don't work out as nice as it does in the separable case. That is true.